Hello everyone, welcome to the video. Today we are going to discuss the problem longest palindromic subsequence. In this problem, we are given a string and we have to return the length of the subsequence that is a palindrome and is also the longest. In the previous video, we have solved this problem using recursion and top-down dynamic programming approach. In this video, we will discuss the bottom-up dynamic programming approach to this problem. We will also discuss a space optimization of the bottom-up dynamic programming. Further, we will also discuss if somebody asks us to find the actual longest palindromic subsequence and not just its length, how will we solve it? We will go through the thinking process, write the algorithm, and also see the code for each of these steps. So let's start. Also, if you are new to this channel, please don't forget to subscribe. Let's start. To begin with, let us first note down the key things given in the question. We are given a string s and we have to return the length of the longest palindromic subsequence in this string. For example, if this is the string given to us, then the length of the longest palindromic subsequence is 4. How? These 4 b's, these form a subsequence, they are a palindrome, and they are the longest possible such palindromic subsequence, and hence the answer is 4. So if we consider our solution as a black box, we are getting input as string s and we are returning an integer length as output. So what will our function signature look like? Our function signature will look something like this. Before going to the bottom-up approach, let us briefly recap how did we solve this problem using the top-down dynamic programming. So we were given this string and we had to find the length of the longest palindromic subsequence. So we thought, let's try this using recursion. So we thought if the first and the last characters of this string were equal, and if somebody gave us the answer to this middle portion, then answer for the overall string will become m plus 2. But that was the case when first and last characters were same. It is possible that they were different. So we thought of the second case. Now if these were different, then we could have broken this string into the remaining string plus the last character. So if somebody gave us the answer to this problem, the remaining string, the overall answer will also become n. But that was just one way of breaking this string down. We could have also broken it in this manner. And if somebody gave us answer to this, our overall answer will become O. So we will pick the maximum of the two since we want the longest palindromic subsequence. We were then able to represent our original problem and our smaller problems in a common manner using s, I and j. Thus, we were able to break our problem down into smaller problems and were able to establish the relation between answers to our smaller problems and our original problem. This was our recursive relation that we derived, that the LPS of si, j will be equal to x plus 2 if the two characters at start and end are equal, and if they are not equal, then this LPS will be equal to max of y and z. Once we had the recursive relation and we had identified the inputs which were s, I and j, we tried to write the algorithm for it. When we wrote the algorithm, we realized that we will need something called as base or terminating condition for this recursion. Now, we knew that the base or terminating condition will occur when the input is smallest. And here in the recursion, the input was getting smaller in terms of the length of the part of the string that was considered between I and j. So the base or terminating condition was length equal to 1 or length equal to 2, for which we wrote this thing. We also solved the problem of overlapping or duplicate subproblems by using map. We used map to store the answers for our inputs. For example, we stored that hey, for this pair of I, j, this is our answer. So this was our overall top-down dynamic programming algorithm. The next step is to think of the bottom-up. But why do we need to think of the bottom-up approach? What is the problem here in the top-down dynamic programming approach? The problem with top-down approach is the same as the problem with recursion. Every method call occupies some space in the memory, and as the depth of the recursion tree increases, the number of active method calls occupying space in the memory also increases. We don't want that. We don't want our memory to be consumed like that, and hence we need to think of the bottom-up approach. In bottom-up approach, we will still use the insight of the recursion. What insight? That we will still use the answers of our smaller problems to derive the answer for our original problem. But we will do this in a bottom-up fashion as opposed to the top-down fashion. What this means is, first we will be solving for smaller inputs, and then step by step we will move towards solving for larger inputs. That means we still have to store the information that for a pair of I, j, this is our answer. Now, what data structure will suit best to store this information? We can use matrix or a two-dimensional array. And if we think about it, two-dimensional array is nothing but just like a map that we had used in top-down approach. Let us now see what does any position in this matrix represent. Consider this one. This position is representing a coordinate I, j. That means in the input string, it represents the part of the string between indices I and j. And what does the value at this position represent? The value at this position will represent the length of the longest palindromic subsequence for that part of the string. So with this in mind, where will our final answer lie? Our final answer will lie here, because here I is 0 and j is at its maximum value n-1. Let us now see how we will fill value at any particular position I, j. Let us say we want to fill the value at this I, j. Now we know that value at any particular position is dependent on these three. So if this is I, j, where can we find I plus 1, j minus 1? It will be here. Similarly, I, j minus 1 will be here, and I plus 1, j will be here. So from here we can derive x, y and z, and using these three values we can fill the value at I, j. Now we have seen how we will fill value at any particular position. But how will we start filling this matrix? From where we will start? We will start from the base condition. And what is the base condition? The base condition is length equal to 1 and length equal to 2. So where does this matrix, what elements of this matrix represent length equal to 1? All elements on this diagonal represent length is equal to 1. Why? Because all elements on this diagonal have I and j as equal. That means there is only one character of that string that we are considering right now. So this will be the length equal to 1. Similarly, length equal to 2 will be the next diagonal. Length equal to 3 will be the next diagonal, and so on. That means we are not filling this matrix in a simple row-wise manner, but we are filling the matrix diagonally. And what will be the dimensions of this matrix? It will be n cross n, as the length n is the length of this string. With these observations in mind, it will be very easy for us to now write the algorithm. Let us now try to write the algorithm. So what is the first thing that we need to do? First of all, we need to declare a matrix of size n cross n. Next, since we are going bottom up, we need to first fill for the smallest inputs. That means our base conditions. Our first base condition is when length is equal to 1. Length is equal to 1 means I is equal to j. And length is equal to 1 means that there is only a single character. And a single character is always a palindrome. So for length equal to 1, our answer will always be 1. So we run a loop. We iterate from I is equal to 0 to n minus 1. And for length is equal to 1, j will be equal to I. So we fill dpij is equal to 1. That means this diagonal will be filled now with value equal to 1. Our next step is to fill for the second base condition. Our second base condition is length is equal to 2, meaning this next diagonal. And how will we fill the values for length is equal to 2? For length is equal to 2, we will check the values of the two characters. If they are equal, that means they are palindrome. So the length of the longest palindromic subsequence becomes 2. But if they are not equal, then the length of the longest palindromic subsequence remains 1. So we again iterate from I is equal to 0 to n minus 2. Now since length is equal to 2, our j becomes I plus 1. And dpij's value becomes 1 or 2, depending on whether the two characters are equal or different. Our next aim is to fill for lengths 3 to lengths n. With length 2, this second diagonal was also filled. Now we will keep using these values to fill the next diagonals. So to fill from length 3 to length n, we know for sure that we will have to iterate, and in every iteration we will have to fix a particular length. Now for a particular length, there can again be many substrings. For example, there can be many substrings of length 3. So to iterate over all of them, we will have to run another loop, and in this loop we will fix the starting position of that substring of particular length. So here we will iterate from I is equal to 0 till n minus length. Now we know the starting position I and we know the length, so we know what will be the value of j. Now we have I and j, so we have to fill the value for a particular ij, and we know how to fill it. We will first check if the two characters at I and j are equal. If the two characters are equal, then we know our value will be x plus 2. And how do we get x? X will be equal to dp I plus 1 j minus 1. So we can fill this value. And else, if the two characters are not equal, then our value will be max of y and z. How do we get y? Similarly as x, y will be dp of I j minus 1 and z will be dp of I plus 1 j. Then we can fill the value dp ij. Once we are done with all the iterations, we can return our final answer as dp0 n minus 1. Now, this is a completely working solution for the bottom-up dynamic programming for longest palindromic subsequence. What will be the time complexity of this solution? The time complexity will be big O of n square because of two nested loops, and same will be space complexity, big O of n square. Let us now go through the code for the same algorithm that we just discussed. You can also find the link to this code in the description. So first of all, we declare a matrix dp of size n cross n to store the results. Then we fill for the first base condition for length is equal to 1. To fill that, we iterate our I from 0 to n minus 1. Then for every I, j will be equal to I only because length is equal to 1. Then we fill dp ij is equal to 1 since single character is always a palindrome. Next we fill our second base condition. Our second base condition is for length 2. We again iterate I from 0 to n minus 2. Then our j's value becomes I plus 1 since length is equal to 2. Now for length 2, we first check if the two characters are equal. If the two characters are equal, then those two characters form the palindrome and dp ij's value becomes 2. Otherwise, its value becomes 1. Once we are done with the base conditions, we move to compute the values for length 3 to n. So to compute the values for every length from 3 to n, we again have to iterate. And in the first loop here, we fix what is the length of the substring that we are dealing with. Then for every length, there can be many substrings in the string. So in the second loop, we fix the starting position of those substrings for that particular length. So here we have a particular length and a particular starting position. Using that, we can compute what will be our j. Now, to fill the values of dp ij here, we first check if the two characters are equal. If they are equal, then our value will be x plus 2. So we calculate and put the value in dp ij. Otherwise, our value will be max of y and z. So we again calculate and we put that value in dp ij. Finally, when we are done with all the iterations, we return dp0 n minus 1. So this is the full working code of the bottom-up dynamic programming approach to longest palindromic subsequence. So far, we have focused on finding the length of the longest palindromic subsequence. But there could also be an extension to the problem. The extension could be that we could be asked to print the actual longest palindromic subsequence and not just its length. Now since we have filled this matrix and we have declared this as the length of the longest palindromic subsequence, therefore we should be able to trace what the longest palindromic subsequence actually is using this matrix. We can see that out of the 3 cases of recursion, the only case where the length of the longest palindromic subsequence increases is this one, case 1. Here it increases by 2. And why 2? Because the same character gets added in the front and in the end. In both of these cases, no new character is being added to the longest palindromic subsequence. That means whenever LPS is being formed, it is being formed because of this first case, and it is increasing by size of 2 by adding the same character to starting and end. That means if we start from our final answer here and backtrack to our base conditions while keeping note of the characters that come during this x plus 2 condition, we should be able to somehow reach our longest palindromic subsequence. So our second observation is that we will be backtracking from our final answer to base conditions in the reverse order. Now, since we are backtracking in the reverse order, that means we will get the characters that are farthest from the middle first, and the characters that are closest to the middle in the palindrome, we will get them at the last. So what will be the best way of keeping track of these characters or storing these characters? We can store them in a stack, because stack observes the pattern last in first out. So the last character to go in the stack will be the closest to the middle. Now our path may look something like this from our final answer to our base condition. Now what happens at base condition? At base condition, we will be either at length 1 or length 2. That means we will have the core middle of the palindrome that we are looking for. If we are at length 1, then that single character will be the core middle of the longest palindromic subsequence. And if we are at length 2, then either both the characters or any of them will be the core middle of the longest palindromic subsequence. Now, one last thing. How do we trace this path? How do we move from one position to next? How do we know where to go next from our current position? So we know the value at I, j has come out of either 3, x, y or z, right? Now, if the two characters are equal, we know for sure that it has come from x. If the two characters are not equal, it has come from y or z. Now, which of these would it come from? Whichever is maximum among y or z. So we will always know at I, j that from where we would have come, x, y or z, and hence we can trace the path. With these 5 observations in mind, let us now try to write the algorithm. So what will be the first step? We will be starting from this position and we will be backtracking our path. To backtrack the path, it is clear that we will iterate. And till when we will iterate? We will iterate till we reach the base conditions. So we start from I equal to 0 and j equal to n minus 1, that is this position. And we iterate till j minus I is greater than 1. Why? Because j minus I equal to 0 and j minus I equal to 1 are our base conditions. Now, in every iteration, we will be at some I, j. What will be all the information that we will have at our hand? We will know I, j, si and sj, both the characters. We will also know the values of x, y and z because this matrix is already filled. Now, what is our aim in every iteration? In every iteration, we want to check if this condition was held true. Because if this condition was held true, then we will need to store the characters that were contributing to LPS. This condition will happen when the two characters at I and j are equal. If these two are equal, we will push this character in the stack. We are pushing this character in the stack so that we can store them somewhere because we will use them later to form the actual palindrome. Now, we are done with tracing the character. The second aim is that we want to figure out that which is the next position that we should move to.
So if the two characters were equal, that means we used x to fill the values of I, j. So what will be the next position to move to? I plus 1 and j minus 1. And if the two characters were not equal, that means there were no new characters that were added in the LPS. So we don't need to add anything to the stack. We just now need to go to the previous position. The previous position will be either from y or from z. So if y was greater than z, that means we would have gone to y. And going to y means j is equal to j minus 1. Otherwise, I is equal to I plus 1, we'll go to z. So this way, this loop will continue to go on. And this will break out of the loop only when this condition is not satisfied. That means we have reached the base condition. Now, when we have reached the base conditions, we will have all the characters in the stack that were part of the palindrome except the very core middle that we will get from the base conditions. Now, in the base condition, we may reach at a point where j minus I is either equal to 0 or it is equal to 1. If it is equal to 0, that means we are left with the single character. So that single character will become the middle string of the palindrome that we are looking for. And if j minus I equal to 1, that means there are two characters. So if the two characters are same, then both combined will become the middle string of the palindrome we are looking for. But if the two characters are different, then any of them can become the middle string of the palindrome. Now our aim remains, how do we use this middle string and the characters in this stack to form our required palindrome? It is very simple. Let us say we had in our stack CBA from top to bottom and our middle string value was D. Then what will be the palindrome that we are looking for? The D will be placed in the middle. Then since in the stack the topmost character will be the one that is closest to the middle, so we will put C at front end and back. Then after putting C, we will put the next character B and then we will put the next character A. So this will become our whole longest palindromic subsequence. So using this algorithm, we can also print the actual longest palindromic subsequence in addition to its length. Let us now come back to our original problem, where we were dealing with the length of the longest palindromic subsequence. So what was the space complexity of the algorithm that we used? The space complexity was big O of n square because we used this two-dimensional matrix. Now let's see, can we solve it in lesser space than this? We know that to fill the value at a particular I, j, we need these three elements x, y and z. Now these three correspond to these three elements on the matrix. Now we know that we have filled this matrix diagonally. Every diagonal corresponded to a particular length of the string. Now for this element, we know that we need only these three elements, which lie only on the previous two diagonals. Now here n is just 5. N could be in thousands or even millions. Now for such large input, filling a particular element, we don't need anything apart from the previous diagonals. We don't need any elements information which lie prior to the previous two diagonals. This is the insight that we are going to use. We can represent these two diagonals as two one-dimensional arrays. This can represent the previous diagonal and this can represent the second previous diagonal. And the value I, j we are filling, it will lie on the third diagonal that we can represent by third one-dimensional array called current ARR. Now, if we can solve the problem using only these three one-dimensional arrays, instead of using this matrix, we would have solved this problem in big O of n space, which will be a very significant improvement. Now, before solving this, let us first try to understand what these arrays and all represent. So since each of these arrays correspond to each of these diagonals, let us try to understand what does any particular diagonal represent. Any particular diagonal represents all substrings of a particular length. Consider this third diagonal. What does this element represent? This element represents that the substring begins from first B and ends at third B. What does this element represent? the substring begins from second B and ends at A. This element represents that the substring begins from third B and ends at last B. All of these three are substrings of length 3. So these arrays will also represent all substrings of a particular length. So if we are currently filling the substring of a particular length L, then this array will hold the values or hold the answers for substrings of length L minus 1, and this array will hold the answers for substrings of length L minus 2. Now let us try to see what does every element of this array represent. Again, consider this third diagonal. These three elements have now become part of this array. Though we have kept its size to be 5, but the rest 2 will be of no use to us because there are only 3 elements in this diagonal. Now consider this first element. This first element means that its substring starts from I equal to 0. Second element in this diagonal means substring starts from I equal to 1. And third element in this diagonal means substring starts from I equal to 2. All of length 3. And these 3 elements correspond to these 3 elements here. Therefore, every position in each of these arrays identifies what? It identifies a unique substring. Using what? Using a starting position and a particular length. Just like this matrix, but every element in this matrix identified a substring uniquely using starting position and an end position, while every element in these arrays identifies a unique substring using starting position and a fixed length of that substring. So what will any value at any of these positions will represent? It will represent the answer for that substring, meaning it will represent the length of the longest palindromic subsequence for that substring. Now let us see how will we fill the values in this array using the values from these 2 previous arrays. Let us say we are filling the value at this position. Thus, for the substring that starts with I and has length L, we want to fill the value of the length of longest palindromic subsequence. Now for this we need x, y and z. Now if this position corresponds to I, j, then x corresponds to I plus 1 and j minus 1. That means x will lie on the length L minus 2 diagonal and at position I plus 1. So x will correspond to this value. Similarly, y will correspond to this value because it will lie on the length L minus 1 diagonal, and z will correspond to this value. So now we know how we will use these previous 2 arrays to fill the current array. But how will we start? From where we will start? We will start from the base conditions. We will fill this first array with the values for length 1, and we will fill this second array with the values for length 2. For length 1, we know that all of the values will be 1 because single character is always a palindrome. And for length 2, our values will be 1 or 2 depending on whether the 2 characters are same or not. So we will have initial values in both of these arrays. And then we can fill this third array as we move forward. Now let's see how do we use all of this to find our answer, the length of the longest palindromic subsequence. So we start with lengths 1 and lengths 2. That means we have filled the 2 diagonals first. We will use these to fill our length 3. That means we will use this to fill our third diagonal. Now once we are done with length 3, what is our next step? Our next step is to fill for length 4. Now to fill for length 4, we need length 3 and length 2's answers. That means we don't need length 1 answers now. So we will dump the length 1 answers. And we will fill this array with the length 2 answers, which were earlier in the previous ARR. And we will fill the previous ARR with length 3 answers, which were earlier in current ARR. Current ARR will now be empty for filling length 4's answers. And so on we will keep on iterating till the time we reach here, and we will fill this final position. And when we reach here, we will return previous ARR's first element because there will only be one element in this one meaningful element in this array to return finally. So this is our final observation, that after every iteration, second previous ARR, this array will hold the values that were present in this, and this array will hold the values that were present in the current ARR, because we only need the latest two lengths. With all of this understanding, let us now try to write the algorithm to solve this problem using these three arrays. We will first declare three arrays: second previous ARR, and current ARR. Then we will fill the second previous ARR for length 1. We will fill previous ARR for length 2. Then we will iterate from length 3 to n. And in every iteration, we will fill the values in current ARR corresponding to the current length. And we will use second previous ARR and previous ARR to fill current ARR. Now to fill the values in current ARR, we will again have to iterate from I is equal to 0 till n minus length. Then we will fill the value at current ARR I using x, y and z. And how we will derive x, y and z from these two arrays we have seen in the previous slide. Now which of these will be used will also be dependent on whether the two characters are equal. But the summary is, using these 5 elements which we know, we can fill the value current ARR I. Once we are done with all iterations in this loop, we will copy all the values of previous ARR into second previous ARR, and we will copy all the values of current ARR into previous ARR. And the earlier values that were present in second previous ARR are of no use to us, so they get dumped automatically. And once we are done with all the iterations for all the lengths, we will return previous ARR 0. This will have our length of the longest palindromic subsequence. And this we have solved with only 3 one-dimensional arrays, that means big O of n space.
Let us now see the working code for the same algorithm that we just discussed. You can also find the link to this code in the description. So first of all, we declare the two arrays, second previous ARR and previous ARR, both of lengths n. Then we fill for the base conditions. So for length 1, we fill in the second previous ARR with all the values being 1. And for length 2, we fill in the previous length ARR with values 2 or 1 depending on if the two characters at I and j are equal. Once we are done with this, we also declare the third array, new ARR, and now we iterate from length 3 to n. Now for every length, we again iterate for the starting position. The starting position can range from I equal to 0 till n minus length. Now we know the starting position and we know the length, so we can calculate what will be our j. Now we have uniquely identified the string, substring, for which we are filling the answer. Now if the two characters at I and j are equal, then the new ARR I, which corresponds to the substring that starts with I and has length, this can be filled from x plus 2. And where will x lie? At the second previous ARR. And if the two characters are not equal, it will be filled using y and z. And y and z both will lie in the previous ARR. So we fill the new ARR using these two arrays in this manner. And once we are done with it, we copy the previous ARR values into the second previous ARR array and the new ARR values into the previous ARR array. Once we are done with all the iterations, we return the previous ARR 0. There is one edge case also that we have to handle. That edge case is that if the string is of length 1 only, then we won't even go till previous ARR. But if the string is of length 1, then we know that the answer is 1. So we return that. So this is the overall code for longest palindromic subsequence using bottom-up dynamic programming using space optimized space, big O space. This is it for this video. If this video was useful to you in any manner, please let us know by commenting below. Also let us know in the comments what will be the next problems that you would want to see on this channel. Please don't forget to like and share the video and subscribe the channel. We will meet again in the next video with some other problem. Thanks for watching.